For those of you that were here last night, I hope you all enjoyed the hog roast and getting to watch the football and so forth. So today we have I think, of a very interesting program. We'll have talks that will be covering the statistics of networks, part of the communications program that's been ongoing over the entire course of the last 6 months. So this is one of a number of different workshops that have been held since January of this year in the general area of stochastic processes in the communication sciences. And this particular program, I think, is going to be very, very interesting because we have people from a bunch of different communities here. We'll have talks on coming from the statistics angle, people that will be looking at social networks issues, people will be looking at communications networks, statistics issues, even I think we have at least one speaker from an epidemiology department, so we have a very eclectic, interesting group of people, I think, gathered for this workshop. Let me also thank the principal organizers of this workshop. That would include Sid Resnick, Daryl Veach, Don Towsley, and Rob Nowak. So I really appreciate all of the efforts that they put into organizing the workshop and finding the speakers that will be speaking over the next couple of days. So without any further ado, I'll hand off to Sid here.
Thanks, Peter. Have you ever noticed that Peter's never early and also never late? It's right exactly at 9 o'clock. Beautiful. First speaker is Haipeng Shen from North Carolina, Department of Statistics and Operations Research, and he'll talk on robust estimation of self-similar parameters.
Thanks, Sid. Good morning, everyone. So just, I want to take this opportunity to thank the organizing committee for putting this very nice workshop together and for having me here to talk. I really enjoyed yesterday's program and as well as the afternoon arrangement of being able to watching the football games and the party at night. So in some sense, it seems to me it fits to talk about this here. The reason is a few years ago I came from North Carolina. There's very nearby there's a U.S. National Institute called Statistics and Applied Mathematics Science Institute, which is called SAMSI. So a few years ago they run a program on network traffic analysis. That's the first time I got exposed to this, which I just joined the department down in UNC. So at that several people here have gone to that workshops. It's a year-long program, gone to that program. So I got interested in this, and with a few colleagues, we started to think about problem in this area. So this is one of the papers we worked on, and with Thomas Lee, who is now at UC Davis, and Zhengyuan Zhu, who used to be my colleague at UNC, now he's at our state. So basically, we're going to talk about robust estimation of self-similarity parameters in network traffic. So I'm going to start. So here's the outline. I want to motivate first what the problem is, then move on to talk about the parameter estimation part. So how the background, how we come up with the parameter and the procedure that's involved. Then I'm going to illustrate the performance of this estimate procedure using simulation studies and real trace. Okay. So this is one of the traces we analyzed. It's a 2-hour-long trace. It's basically a packet count of traffic on this Abilene backbone network between Kansas City and Indianapolis. So it's for every 100 millisecond, there's you count sort of some device will be able to count how many packets was transferred on this link. So this is 2 hour long, about 2 hour long. So what happened now? Basically, this is a plot of the time series across time, and what you see here is you see the sort of very common up spikes and valleys and sort of peaks on network traffic sequence. So basically, when people analyze such of trace, a few concepts or terms appear very often, and the first one is long-range dependence. So basically, if you have a second-order stationary stochastic process, say xt, if it's long-range dependent or RID with the parameter alpha, if it's one of the definite characterizations of this process is through the autocorrelation function. basically has this type of tails as the k increases. Notice alpha here is between 0 and 1, so basically this autocorrelation decays very slowly, and in the end what happens is that if you sum them up across all the legs, it diverges, it's infinity. So basically at 2 time points are even very far away, they still have a strong correlation. So that's why it's called long-range dependence. Is sort of on the other side of this common time series, which we saw more often short-range dependence. Another characterization is through the spectrum function. Basically, near the origin, nu here is the frequency. So near the origin, it has a power law type of behavior over here. The existence of long-range dependence makes some of the statistical analysis harder, much harder to deal with. One of the simple example here is if you think about estimating the population mean using the sample mean, and if you want to calculate the variance of that sample mean of that estimator, in the traditional case, it's basically the variance over n. And over here, if the x sequence is long-range dependent, basically this variance has this form, and has the 1 over n factor here. Then you also have the alpha, which is the scaling exponent here, appears in the scalar as well as this constant for the autocorrelation function. So what this tells you is, in order to be able to, so this is an example where it modes with that both parameter alpha and this c sub gamma are of interest in analyzing this type of sequence. And this book is has a collection of papers that talks many aspects of this type of sequence here. Another term that appears very often is self-similarity. Basically, if you have a time series of a process which is self-similar if and only if it satisfies this equivalence. So basically, if you sample the time points according to a different scale, and basically you see the same thing except you scale them by multiplying this factor. Okay. So this h here is called self-similarity parameter, or sometimes called Hurst parameter. As it happens, people have done, like Walter Willinger here has some seminal work basically established that this existence in the network traffic, in analyzing network traffic. And there's also a close connection between long-range dependence and self-similarity. For basically, if the yt has it's a self-similar process and has a finite variance, and also has this Hurst parameter between 0.5 and 1, then the increment of this process yt basically is long-range dependent. And also the two parameters, the long-range dependent parameter alpha and the Hurst parameter h, has this relationship. Okay, it's a sort of very nice linear relationship between them. So basically, this puts these two parameters very close related, and that's why sometimes you hear people talking about sort of these two parameters or these two type of processes in the same context. Where a nice example is for to model this. Nice example for the self-similarity process would be the fractional Brownian motion. Then the increment of this process is something called the fractional Gaussian noise, basically, which is long-range dependent. Okay, so that's an example that I want to use here. So basically, as you can see, the problem I'm interested in is to estimate this either one of these parameters and also this scaling this constant in front of the c sub gamma. Okay. All right. So now I'm going to show you a few traces we used. So this is the same trace, and we applied one of the existing estimators to this trace and got a Hurst parameter estimate, which is 1.19. If you remember earlier in the previous slide, I said if it's between 0.5 and 1, that's usually the range for the trace to have long-range dependence. This is bigger than 1, so it suggests there's some non-stationarity in the sequence. And basically, you can see that there's ups and downs which are more prominent than what this stationary process can have. And this is another trace which is collected at the UNC link, the incoming traffic to UNC. And you can see this bump, this valley here, that's very significant. And as we apply that estimator to this sequence, to this trace, we got a Hurst parameter estimate which is 1.28, which is also bigger than 1. So that's another sequence at the different time periods, a 2-hour-long trace. And in the middle of that trace, you see this big peak. Basically, if you zoom into that region, you see very rapid ups and downs. Okay, and I think my computer science colleagues told me they're suspecting this is some kind of pulse scanning that's going on to create this peak of the packet count. And this is another sequence. Now let me back up. So here, the Hurst parameter estimate is 1.51. And this is a sequence where in the middle, about 10 seconds or 15 seconds, the packet count is very low. It's almost 0. So if I zoom into that region, this is what happens. So it's roughly around this level here, then it sort of drops to almost 0. There's very small number of packets being transferred, and it comes back up. So there's some dropouts of the packets during the collection process. All right. So with those examples, basically I want to motivate that when you look at such traces, there are all kinds of non-stationarities that might appear in the sequence. You could have some trend that are more continuous, like a gradual diurnal trend that depends on time of day or day of the week. Maybe you can approximate that using as polynomial functions, which basically are smooth. You could have very rapid, abrupt mean level shifts, as well as variance level shifts. So basically, you drop to the almost 0, then comes back up very quickly, and the magnitude can be of different levels. So you could have missing values, then the recording device or something happened that didn't record. So there's a well-known phenomenon that this non-stationarity can be confounded with the long-range dependence. Okay, it's very hard to separate these two other different tests that are developed. Try to sort of, is this long-range dependence or is this is caused by non-stationarity? And another thing is, in analyzing such trace, you could also see extreme values, basically both very large, huge values that spikes or very low values. You could call them outliers. For the large values, you could say inliers for the smaller ones. So our goal when we started working on this problem, we basically try to come up with a procedure that's robust against such phenomena, the non-stationarity, and as well as the extreme values. And we also want to try to be able to characterize the type of non-stationarity that appear in the trace. Okay, so this is sort of the final product that I want just to, before I talk about the procedure, I want to give you a sort of idea what we came up with in the end. So this is the sequence I showed you at the beginning, so that has this type of trend. And what we're going to do is we're going to decompose this sequence into these two components. One is what we call level shifts. For now, we're mainly working on the mean. So this is the mean level shifts. It has this, basically it's a stepwise functions that try to capture the underlying sort of change of the level. And after you take that out, that's the remaining trace. Then we're going to model this to get some estimate of the Hurst parameter. Okay, and so this is some diagnostic tool or graphical tool for us to look at the long-range dependence structure. So this solid curve is something called a log scale diagram, and was proposed by Darrell, who is sitting in the back, and his co-author. Basically, this is basically the idea is, I'm going to talk about this in the next few slides. If there's a long-range dependence, at some scales, you should be able to fit a line to this solid curve. And that slope would have to do with the Hurst parameter or the long-range dependence parameter. And this dashed line, which is below it, is something we came up with. Basically, it's follow the sort of similar idea with this log scale diagram, and which is based on this sequence, and also it's using a robust regression technique. sort of try to reduce the effect of the outliers of the extreme values. And again, the way to look at this is try to fit lines to certain regions which are usually in the upper part of this scale. Then that slope has to do with the alpha parameter or the h parameter. Okay. All right, so now let me talk about the parameter estimation. So there are many existing estimators for h or alpha. The earlier ones, I listed a few of them here, which this paper has done a nice empirical analysis of comparison between among these estimators. And our focus is going to be on the wavelet-based estimators. Like I said, Dara and Patrice in 1998 proposed a wavelet-based estimator for both the Hertz parameter h and the constant c sub gamma. And 5 years later, this group of people proposed a slight modification of that estimation procedure. So I'm going to focus on these two estimators. So now let me review this a little bit. So it's wavelet-based. So basically what happens is you're going to consider a family of wavelet basis functions. So starting from this mother wavelet, you're going to do dilation and translation and all that. So you get this wavelet basis function. Now you take a long-range dependent process and you apply discrete wavelet transformation to this process, which give you the coefficients. And the estimate is going to be based on the sequence of coefficients. So in this paper, there's some assumptions of, but if you in certain circumstances, you can assume these coefficients at the same. J here is the index for the scale. Their ID Gaussian for fixed scale. If you look at the same scale, all the wavelet coefficients at that same scale have this property, and if you look across scales, they're independent when the scales are different. And for large j's, basically for j's between certain region, this expectation of the square of the coefficient has this expression. It's basically equals 2 to the power of j times alpha. Alpha is the LRD parameter times some constant. Okay, so that's, and the estimation procedure is going to be based on this equation. Okay, so that's the expectation of the squared wavelet coefficient at scale j. It has a very nice relationship with the scale j, and as well as the alpha, the parameter alpha. Yes.
C sub f.
C sub f. If I go back here. So that appears in the definition of, although that's in the definition of the spectrum function of the. Okay. See here. All right. So now, if we take this, keep in mind we're trying to estimate alpha here. So it looks like the natural thing to do is to take logs on both sides. So that's. We take log base 2 on both sides. We have, on the left-hand side, we have this quantity. On the right-hand side, we have a linear expression with the j being the scale and alpha is the slope of the. So if you, this looks like a regression type of equation where you have j would be the independent variable, the predictor, and you have, if this is unknown, but if you have some estimate for it, this would be the response, and you basically fit a regression, you get estimate for the slope, which would be alpha. At the same time, you get estimates for this CF times C, and you can work with it to give you estimates for CF as well. Okay. Now, to estimate this expectation, what Dara and Patrice proposed is to look at the sample average. Basically, this is like sample variance at scale j, and n sub j would be the number of coefficients at scale j. So this, keep in mind, this is the wavelet basis. As you move up the scale, every time you sort of reduce the number of coefficients. So this is the number of coefficients at scale j. And then you put this in here, and you say, let me take log 2 of that, and approximately I should have this equation. And because these are Gaussian with mean 0, and basically this is chi-squares, and you have summation of square of the normals, so that's where you have this term for the errors. And so basically what this happens, this is a log 2 of the sample mean, sample variance. And what we have here is, if we take expectations on both sides, because the expectation of log 2, the expectation of the log doesn't equal to the log of the expectation. So you have this term, which is here, then you have some bias correction term, G sub j, which you can actually calculate explicitly, and then you get the variance of the response as well. So now what this suggests is to correct, so G sub j is something you can actually calculate. You can actually correct for the bias by subtracting that from this response, and then you treat that as y sub j, and you consider a linear regression which is of this form, and then you, so this is error, has mean 0 with this variance. Okay. So the estimator basically is going to work by fitting a weighted least squares to this regression. By fitting these, get a weighted least square estimate of the slope, and the weight is determined by the variance of the error. And then once you have alpha hat, and you can plug it into this linear relationship to get h hat. Okay, so that's what this method works. And as a way to show this regression sort of through a graph, they propose this log scale diagram, which is a plot of the y sub j at the j scale against the scale j here. And so here is, I'm plotting server things on this plot. The trace behind this plot is a synthetic, is simulated fractional Gaussian noise plus some level shifts. Okay, and I'm going to show you how the model in a few minutes, but that's basically how this trace was simulated. And let's see, the dash curve here, the upper one, is the log scale diagram for this trace. By applying the previous procedure, get yj and you plot it against j. So if I were to get the estimate for the alpha, I would find an upper region that seems to be linear, sort of intuitively speaking, then fit a regression line to that and look at the slope. So if you look at this plot, it would be this region, probably from this point up, and you fit a line to it. The slope would give you estimates for the alpha. Then there are some other ones. The solid line here is, since we know the theoretical model for the trace, we can actually calculate the log scale diagram for the fraction Gaussian noise exactly, and that's the solid curve. And those vertical lines give you the variance band at each scale. So you see there's quite a significant difference between what you actually get from the trace versus the theoretical one. And the dotted curve, if you can see it here, is very close to the true log scale diagram, which is after you apply the procedure I'm going to describe, then you calculate this again. So it's very close to the true underlying process. Okay, and by this plot, I also want to mention a very important issue here is to find the region that you can fit this regression line to. So basically, that problem was analyzed in these two papers. Try to select the starting point of this long-range dependence region that you can fit the regression line. Sometimes you actually have to select the ending point as well. But these two papers studied the starting point of this process. Okay, so that's basically the first wavelet estimator. And keep in mind what it does is you take the sample average of the squared coefficient at each scale, then you take the log. Okay. Now this 2004 paper basically proposed a slightly different way to estimate alpha by using similar ideas but doing the log and the expectation in a different order. So this was done by, you take the squares of the coefficient at the j scale, and there are nj coefficient at this scale, and you sort of divide it into two groups, and the first part and the second part. Each time you take the one from the first part, and you take the first one from the first half, you take the first one from the second half, then you take the average, and then you keep doing that. So this gives you d sub jk. Okay, then you take log of that, and what you end up getting is you have the same mean term here, the j alpha, the log 2 CFC, and you have a different error distribution, which is, since you're adding two chi-squares, you have this log of the chi-square. X sub 2 here is the chi-square with the 2-degree freedom, and over this denominator. And as it happens, you can find this has a negative Gumbel distribution by taking this log gamma chi-squared 2. And with this mean and this variance. But the nice thing is you also know the exact expression for the mean and the exact expression for the variance. Okay, so now you take this logged sort of coefficient squared and average, you average it again. So this is the delta sub j. Now once you take the first average, you take log, you only have nj over 2 of them left. You have this delta j here, which has this expression, which is the j sub alpha plus log 2 CFC. That's the same component we saw earlier, and now you have a different. So this error is the average over a lot of negative Gumbel distributions, distributed random variables, and they apply central limit theorem. So they say if you average over enough number of these pairs, you have this can be approximately treated as normally distributed random variables with this variance and mean 0. Okay, and then after that you're going to apply weighted least squares to this regression and get estimate for alpha. Okay, so that's how the group in 2004 proposed to do. Basically, the difference is in the first proposal you take the mean and you take the log. In this proposal they take log first and then take the mean. So in their simulation, I think they considered fractional Gaussian noise traces. They did simulation. They didn't analyze real data. They only look at the simulations. This slight modification of estimator works slightly better than the original estimator. I think and one of the reasons is by taking the logs first and the average, you might make this a little more robust to the heavy-tailed fluctuations, the extreme values. And this actually was noted earlier in 2002 by this group of people, that you take log first and then take the mean. Okay, so basically these two wavelet estimates are very similar. So from now I'm going to treat them more or less the same. So they have some very nice properties. Basically, because of the property of the wavelet basis, it naturally incorporates the scaling phenomena, and it's unbiased and asymptotically efficient. So because of the use of the discrete wavelet transformation, the calculation is very fast. And also it's robust to polynomial trends. Depending on the number of vanishing moments you use for the wavelet basis, you can make this robust to different orders of polynomial trends. And later, Darrell and Matt showed this estimate also robust to moderate level shifts in the mean as well as the variance. So if the level shift in the mean is not huge, and also the shift is somehow smooth, this estimate is actually very robust to those type of things. So let me spend a few minutes on that. So what they considered is this class of non-stationary long-range dependence models. So the W here is the basis process, the basic process which is mean 0 with unit invariance, and it has a long-range dependent parameter or a Hurst parameter H. Then you scale that by multiplying a variance function or standard deviation function, sigma t. Then you add a mean function to that. So now you make this process it's non-stationary both in the mean and depends on what the m looks like what the sigma looks like. It could be non-stationary in both the mean and the variance. And then they consider a specific model which is a smaller set of this by modeling mean level shifts. So it's this MT is modeled using this T function which has this form. So what it means is, so this is the arctangent function which has this form. It's between negative pi over 2 and positive 2 pi over 2. And L here is the location of the level shift. And the J is the scale, is the size of the level shift. So if you, S is the smoothness of the shift. So basically it controls how smooth the shift is. Let me give you some pictures I took from their paper. So this picture basically says I have, say, 16,000 time points, and in the middle of that I have a level shift at the time point 8,000, and then that's the size. So before the level shift, the level is at 1. After that, level is at 2. And then you see different curves. That is controlled by the S. It's basically the smoothness. When the smoothness is 0, it's discrete. It's discontinuous. So basically, you see the level is here, then it jumps right up to that higher level. And as you increase the smoothness index S, you get transitions that are more and more smooth. Okay? And this is for the largest smoothness index, 1200, and that's a simulated fraction Gaussian noise sequence. You see the transition is just very smooth here. So then they did simulation based on those models. They simulated sequence, and then they applied the wavelet estimator to the simulated sequence and showed the nice robust property of the estimators. So I highlight a few points here that I want to draw your attention to. One, so there are two H parameters, H equals 0.5, H equals 0.8. When S is 0, that's the sharp jump. And J controls the scale, or the size of the jump. So when J is 4, it's the biggest jump we considered. So that's the stationary estimate if you take out the level shifts. The truth is 0.5, so that you get almost 0.5, exactly 0.5. And on this is by applying the wavelet estimator and directly to the non-stationary sequence, you have the mean is 0.5. There's some bias, and which is larger when the size of the jump is larger, when the jump is less smooth. So those are I want to point you to. Then as the transition gets smoother and smoother, you basically see the estimator is very robust. They also consider variance shift, the shifts in the variance. What they found is it doesn't have a large effect on the estimation. Basically, it's very robust. So what happened is when you change the variance, you basically imagine that log scale diagram. You're shifting the whole curve up and down, and when you face regressions, the slope doesn't change much. But when you add the mean level shifts, you're going to change the tilt of the log scale diagram. So there's very nice robust properties of this estimate, but it does exist some problem when the jump size is large, especially when it's very discontinuous. So those are the things that we want to consider and see whether we can make the estimate more robust. And we also want to consider multiple shifts instead of one. And another thing is we want to be able to estimate the location of the shift and the size. Okay. All right. So here, let me get into describing how this procedure works. Is we're going to model. So this is very similar to the mean level, the non-stationary model that are used. I have the mean alpha t, and beta t is the stationary long-range dependence process with the Hurst parameter h. And alpha t is here, but we're going to consider it as stepwise functions. So it has mean level shifts. And what we don't assume is the location of the mean level shifts are unknown. So this t's index the location of the jumps, and the mu I is the size of the jump. So we're gonna all of this mu I and the t's are unknown parameters which we have to estimate, and h is also unknown that we want to estimate as well. Okay, so there are a couple of problems. One is we have to select the model. So we consider stepwise function for the mean, and we have to select the number of jumps and as well as the location of the jumps, and then we have to estimate the h.
The t's are deterministic.
Which one?
The little t's.
Little t. Those are deterministic, right? And which? Okay, so basically, this is a model. We model this as a model selection problem. So first, let's define. We have to define what's the optimal model or the best model we want to estimate. So basically, in order to get that model, we need to find the best combination of the m, which is the number of jumps, as well as the location of the jumps. So the way we did it is we consider this as a model selection problem. We use some model selection criteria. Here I'm going to show you is something called a Bayesian information criteria, BIC. Basically, it's a balance between the log likelihood and the complexities of the model. Okay, so it has these two terms. The first term is a -2 times the log likelihood, which in this case is the conditional log likelihood, conditioning on knowing the Hurst parameter h0. So here it's at this level, I assume it's known. Condition on that, you come up with the log likelihood. Then the second term is you have this log n is the size of the sequence, then you time 2m minus 1. 2m minus 1 is m, is the number of jumps. Then you have, m is the number of sort of segments. So it's m minus 1 would be the number of jump points. And at each point, you have to, after each jump, you have to estimate the mean level. So there's another m parameter you need to estimate. So that's the total number of parameters we want to estimate. But you can see it's the balance between the model size. As you increase m, it gets more and more complicated. And also, at the same time, you want to balance that with the -2 log likelihood. OK, so now suppose the beta t is, depending on the model you have for beta t, and this is in some sense parametric that since you need to use the log likelihood. If the beta t is a fraction Gaussian noise with the Hertz parameter h0, you can write this log likelihood exactly this way. And now the best model we're going to define would be the m and t combination that minimizes this BIC. OK, so once this m and t is determined, then you can estimate the mean level by the sample mean within each segment, and you put that together. That gives you the estimate for the stepwise function, and you also get the residual sum of squares, and so on. But this depends on, in order for us to be able to calculate the BIC, it depends on the initial value of h sub 0. So you have these 3 parameters. So it's sort of cyclic argument where we consider a set of initial candidate values for h0 between 0.5 and 1. Okay? And then we derive, for each one of them, we derive the best model under each candidate, and then we compare the BICs to select the h0 as the one that minimizes the BIC, and the corresponding m and t will be used in estimating the final model, as well as getting the final estimate of h. So this is like a stepwise procedure for the estimation. Now, to come up with the best model for m and t, you can imagine the computing effort is very heavy, because you have the n is the size of the trace is typically huge, and m varies. So we don't have a fixed set of m's, the candidates for the jump sizes. So what we end up doing is we proposed sort of a greedy merging algorithm. We started with some model that's obviously is overfitting, then so we shrink it. Then we get a nested sequence of models, and we sort of select within that nested sequence of models. Here is how, so basically you can imagine at the beginning, see every other time point there's a level shift. So that reduced it by 2. And at each step, I'm going to pick 2 segments that are next to each other, and I'm going to merge it. Once I merge it, it's going to increase the residual sum of squares. Okay? And I want to pick the merging at the points where its increase is the smallest. Okay, so that at each level, each step I merge 1, then I move on to the next step, until at the end, there's only 1 segment for the whole sequence, so there's no level shift. So as you get a sequence of these models, which have different sizes, which have different residual sum of squares, which is related with the log likelihood, so you can pick the smallest BIC from this sequence. Another thing, the way this is nice is because every time you're merging 2 segments and next to each other, you actually can update the criteria, which is the residual sum of squares, very efficient. You don't have to deal with all the other segments that are not involved. You only need to update that locally. So that can be very useful in terms of the computing speed. So that's the first part, where basically gives us estimates for the alphas. Now we're going to estimate the h for the beta. But here, instead of using the weighted least squares, we want to do something that's more robust, which is we're using robust regression techniques. So I have time until 40, 45? 45. So let's say this is a linear model. I have the beta is the slope that I want to estimate, and the least square regression basically try to minimize this residual sum of squares. And that's basically the basic idea, or the key idea for the first 2 wavelet estimators. But when the errors doesn't have a Gaussian distribution, or have a distribution that has heavier tails than Gaussian, the least square procedures can be very unstable and robust. So we want to replace this by using some robust regression technique. So okay. Let me skip this. So these are some robust regression techniques we considered. The first one is a L1 regression. Basically, instead of replacing that squared using L1 norm, which in some sense, imagine you estimating the center, and this would give you the median as the center, while the other one gives you the mean as the center. Now you can do a M estimation, which basically, instead of using this residual, the error term, square it, you can apply some function to it, and that function has this bell-shaped curve that reduces that downweights the extreme large errors. And that can be estimated using this iterative reweighted least square procedure for the estimation. Or you can trim it. You have the squared errors. You can look at, instead of looking at all of them, you can look at a subset of the squared errors, just look at the smaller one, which basically is based on the order statistics of the errors. So those are the things we consider. Or another thing you could do is do something called a quantile regression instead of just fit quantiles. Now, so putting all those things together, what we are doing is we first remove the level shift. In the end, we get some estimate for the beta part. Then we're going to apply the wavelet transformations to the beta traces and then estimate the wavelet coefficients from the, and estimate H using a robust regression technique. And then, so as an analog tool for the log scale diagram, we're going to, instead of plotting Yj versus J, we're going to plot a robust center of the wavelets, the coefficients, because we're doing robust regression, we want to see what the robust center is, then connect them and see how. So this is the result from applying this technique to the simulated sequence. Okay, so now let me show you some numerical results. So for simulation studies, we consider 3 different setups. The first one, all of them are related to the fractional Gaussian noise. So the first one is fractional Gaussian noise. Second one is the fractional Gaussian noise sequence with some missing values, either at the beginning or in the middle. Okay. Or the third one is, which is the more interesting one, is we add different amount of level shifts to the sequence and see what's the effect of that. So we consider the H equals 0.5, 0.75, and 0.9. And for the fractional Gaussian noise sequence, we consider this wavelet estimator and all these robust estimators. But basically, the difference among these procedures is how you're doing the regression, whether you're using least squares or you're using the robust regression. And then just to check how our level shift removal procedure works, we apply the same procedure as well, and which in most of the cases is found no level shifts or very little, very few level shifts. So those are some examples of the simulated sequence. As you see, as H increases, you see some oscillations. You can imagine you can mix this together with the non-stationarity. So this is a comparison. Basically, the point is all of them do very well with fractional Gaussian noise. The robust ones has slightly smaller bias. If you look at as H increases 0.05, 0.02, 0.06, 0.02, but all of them are very small. Okay, so the increment. Now, so then we try to see how, because one of the traces we analyzed has this missing value in the middle. So we want to see how that works. So we, on purpose, dropped out some time points in the beginning, some time points in the middle, which is 1% of the sequence. And then we applied the procedures. So here, based on the first study, we see all the robust methods work pretty similarly. And this iterative reweighted least squares is more efficient. It calculates faster. So we are using this one. And then here we're applying the wavelet estimator, the robust regression, and also the level shift plus the robust regression. So what we're seeing here is the missing value has a bigger effect if it happens in the middle. And if it happens in the boundary, it has a smaller effect. What happens is for the wavelets, when you calculate the wavelet coefficient, you're actually dropping some of the boundary points. So that's that. And you see the robust methods actually reduce the bias. And all the procedures have about the same standard errors or standard deviation for the variability is about the same, but the bias is different. Okay, so here's the last one. where we consider level shifts. So we take the simulated fraction Gaussian noise, we add some stepwise functions to it. For h equals 0.5, 0.75, we consider the level of the size of the level shift would be 1 unit of the grand mean. So we calculate the grand mean, we add 1 unit of that. And for the h equals 0.9, it's 4 units. Okay, just to be able to separate the natural oscillation from the level shifts. So when we apply the selection, the BIC selection, for h equals 0.5, it selects the number of shifts 98% of the time correct. And when h equals 0.75, 84% time is it correctly selected number of shifts. And when h equals 0.9, 68% of the time is correct. And as you see, for larger h's, it's more and more harder to distinguish between level shifts and the natural oscillations. Okay, so those are the type of level shifts we added. So that's one sequence. And the white line is the level shifts we added. And here it's much bigger. And then I take one sequence from here, when h equals 0.9, and compared the log scale diagram and the robust log scale diagram, as well as the true log scale diagram. So basically, in this case, the robust one and the true log scale diagram are very similar. So that's the comparison between the bias and the variability of the estimates. And this is the wavelet estimates, and that's when we apply the robust method to the raw sequence without removing the level shifts. And the last column is you do both. You remove the level shifts as well as you apply the robust regression. So basically, the message is we did a pairwise test. There's not significant difference between the least square and the robust least square when you have such level shifts. But once you remove them and you combine that into the estimation procedure, it reduces the bias significantly. Okay, so it's a 1 order different in terms of the. Okay, so now, yeah. Okay. In terms of the estimation performance for real sequence, I showed you 4 traces. I apply them to those 4 traces, and this is the Hurst parameter estimates from the existing wavelet estimator, and 3 of them is bigger than 1, and then this is 0.92, and those are the estimates after removing the level shifts, and you see they're quite similar. It's around 0.8. Somehow that seems 0.8, 0.9 seems to be the right. I don't know, it just seems to be the right range of the Hurst parameters for this type of sequence. Now, somehow I have the log scale comparisons, the log scale diagram comparison here. Oh, it's on here, but you couldn't probably see it on the screen. But it's so what happens. Let me just summarize. What happens is because of those oscillations, and the log scale diagram has bumps in them, and it makes the selection of the region very difficult. After you remove them, the log scale diagram seems you can fit a very nice line to it easily. Okay, so we also did some comparison of the subtrace consistency. Basically, the idea is you divide the traces you split it into small pieces, and you estimate the Hurst parameters, and then you see how similar they are among the sequence. So basically, the robust ones give you estimates that are more similar within the same trace than the traditional method. Okay, so that's it. Thanks.
A quick question? Didn't go too far off schedule. Yes, Matt.
So, when you do with the real data, have you done things like change the length of the data and see whether or not you get consistent estimates?
Change the likelihood.
No, take a small subset of the data and then try and re-estimate.
Right. So this, in some sense, this is basically what we did here. We take the whole sequence and split it. So just chop it into 4 pieces, and then estimate the Hurst parameter on each one. So the first row gives you the estimates for each of the piece, and the second row is from the robust method. And you see they're very different. Another thing you notice is, let's take an example here. For UNC1 sequence, the 4 estimates from the wavelet estimator, for 2 of them is one, it's bigger than 1. For the other 2, it's less than 1. and they're more different than the robust method.
And when you do that, do you find the same level shifts?
The level shift was selected using the sort of the procedure proposed in the 2003 paper by selecting the starting point. It's fitting the Q statistic, try to.
But do you find the same level shifts when you take subsegments?
No. Right. They vary. Basically, if that say if the oscillation happens on one subtrace, that's going to affect more for that particular trace than other ones.
I think we better try and stay on schedule. Thanks very much.
Thanks.